I didn't have many time to prepare the presentation, so I will be right on board. So what I want to talk about? So splittings and pullbacks. So first I will talk about the relation between splittings and pullbacks. And then pullbacks are good. And what are exact Lode algebroids? I will explain everything later. And if there were time, I will state some open problems or open questions. Okay, so first of all, I want to start. I'm not sure if everybody here knows some of the basics, but I assume everybody knows what a Lie algebroid is, right? So, the algebroid is a Lie algebra structure. On the sections of a vector bundle, so we start with vector bundles, and you have a Lie algebra structures on gamma of E, the sections of the vector bundle E, and it's assumed that it satisfies the so-called Leibniz rule. That is, if you have two sections, alpha and beta section, and gamma of E, and F a function on the base manifold M, then it satisfies this rule plus something derivating F times beta, and this thing that derivates F is an uncle map, where this row here is a map from a bundle map from E to T of M. That's called the uncle. So this is the definition of a Lie algebroid. So I want to talk about this relation because I have this paper with Henrique and Marinken, where we prove some splitting theorems in the basic structure that is just the splitting theorem. We prove these splitting theorems are Lie algebroids. So this is the starting of this relation between splitting theorems and pullbacks. So this is a Lie algebroid, and we have a well-defined notion of pullback on Lie algebroids. So if you have a map, so let me state what's the pullback. So imagine that you have, let's say, a submanifold M, and over M you have a Lie algebroid. I will just put the bundle here in this picture, and assume that the manifold is transverse to the uncle of O. We call that the uncle is a bundle map here, and this only means that the sum of the tangent space of N if the image of O is the tangent space of M entirely. So when you are in this situation, then if you calculate the inverse image of T of N, this is a bundle over N, is a bundle. And what happens is that you have also a Lie algebroid structure on this bundle. So this has a Lie algebroid structure. So what's the algebroid structure? Is the natural one. Every time you have a section for this bundle here, you extend it to a section of E, and then you calculate the bracket, this Lie bracket that you have here, with these extended sections, And after that, we'll restrict it again to n, and then this is going to be another section of this map here. So it has a natural Lie algebroid structure then. Not just any Lie algebroid structure, but this is the algebroid structure that you get when you extend the sections, calculate the bracket here and the restrictor. So this bundle here is the definition of the pullback when you have a transverse map. But in general, you have to, if you have, a transversal submanifold. But in general, if you have a map from n to m, this map is transverse to the anchor. And this means that the image of the differential of phi plus the image of the anchor is the tangent bundle of m, but only of course on the points that it makes sense. So this is what this equation here, this expression means. And so in general, if you have this thing here, you can consider n as a submanifold inside the product of m times n. And this submanifold is transverse to a anchor of another Lie algebroid over this product. Let me draw it here. So you consider n inside the product m times n. This is in the graph, so phi times the identity. And this is going to be a submanifold here that's transverse to the anchor of this Lie algebroid structure. So there is a product between the algebroid structures, and it's possible to make this bundle here also a Lie algebroid. And then this condition translates in here to this map being a transverse manifold, just in this example. And then this manifold that you obtain using this identification is what we call the pullback of E. This is going to be a submanifold of over M. So it's not every map between M and N you can define this pullback, but under some transversal conditions you can define this pullback. So you have this pullback has some nice properties, like for example, if you have two maps, just draw a picture. The next would be O. Have a bundle here and two maps. And then you can pull back one time it here. You get the algebroid over M. And then you can pull back it again to get the algebroid over N. And one of the nice properties is that this is the same thing as to calculate the pullback of the composition. So if you calculate this pullback, then this is the same to calculate this thing. Note that the notation that I'm using for pullback is just this exclamation point. This is to differentiate the pullback as vector bundles from for differentiate from pullback of vector bundles, because it's not the same kind of pullback. And so this is for Lie algebroids, and the structure. So what do we prove in this paper for Lie algebroids? What's the splitting theorem? What's the splitting theorem for Lie algebroids? Another thing is that the title of this talk is why do we have so many splitting theorems? But I'm assuming that you have so many splitting theorems already. So I'm not giving many splitting theorems for you. Most of the splitting theorems come from these Lie algebroid structures, and that's what's made in this paper. So what's the splitting theorem? So imagine that you have a Lie algebroid over M, and you take a transversal submanifold and transverse to the anchor. Let's call it rho. Then let's draw a different picture. So have this inclusion here, and you have a manifold, a Lie algebroid here, such that n is transversal to its anchor. And then you consider the normal vector bundle over n here, and its projection. Just recall that the normal vector bundle is the tangent space of M restricted to n, divided by T of n. And then you have this projection here, and then you can make this pullback twice. First you kind of restrict it, that's to E, and then you can pull back it to a bundle in here. So, our splitting theorem, or splitting theorems, in the way we understand, would be find some isomorphism between this vector bundle here and this some open setting here, open sub bundle here. So let me say exactly what I mean. So what's a splitting theorem? What's our splitting theorem? So we say that there exists an isomorphism, a Lie algebroid isomorphism that I'm not talking about. Okay. Between this model, local model, and the restriction of this Lie algebroid here. So this is an isomorphism that preserves the bracket, basically, between bundle that preserves the bracket. And this thing here is just a tubular neighborhood embedding inside the open set. So why do you call these splitting theorems? Because when you restrict this, come back here. When you restrict, this is a special case of local splitting, in the sense that locally, this is kind of proving that in some neighborhood of every Lie algebroid is isomorphic to a product of some tangent part times some other Lie algebroid. We're not talking too much about this part here, but this is kind of every Lie algebroid is locally the tangent space of Lie algebroid of some manifold times a singular Lie algebroid. So I'm not entering into the details of this thing here, but I mean, there's a reason why we call it splitting. So this kind of splitting is the kind of splitting that I'm looking for, but not only for the algebroids. So the other paper that I coming soon with Thiago and Henrique, we also prove what we call the analog of this theorem, this splitting theorem, for current algebroids. So I'm not only interested in Lie algebroids. So what types of brackets I'm interested in? So just let me see if it. So for that I have this definition. It is the definition of a Lodai bracket. So a Lie algebroid is a Lie algebra in the tangent space of in the sections of. Sorry. Yeah. A Lie algebroid is a Lie algebra structure on the space of some bundle. So here is something analog, but instead of a Lie algebra, we have a Lodai algebra or in Leibniz algebra. So let me see. It's a bracket. It's let's say bilinear. So I call it A instead of just put the brackets because this is the notation I like more to use the formation. So not sure if it will be useful here, but I'm calling the bracket of A. So A is a bilinear map just like a Lie algebra, but it's not a Lie algebra. Satisfying these two conditions, such that it has also to satisfy the Jacobi identity, just like in the Lie algebra, in the case of Lie algebras, or Lie algebroids. But the modified one, that's the version for Leibniz algebra. It's basically this formula here. Let me write it. And you have some interpretation for these equations, but I don't have time to explain it all. But this is, essentially means that the bracket preserves itself. And we still have satisfied the Leibniz rule. Sorry? Yeah, there's a problem here. Should be a gamma. Thank you. Is that a problem yet? Okay. All right. Let me rewrite this thing. So basically, alpha derivates beta. Here is alpha derivating beta. And then here is, beta stays, and they derivate gamma. Okay. All right. Sorry about that. If you satisfy the Leibniz rule, meaning that if you calculate f of alpha beta still equals f of I of beta, good, plus some rho of alpha times beta, but then it satisfies the second Leibniz rule. And the second Leibniz rule, Lie algebra will satisfy it automatically because it is skew symmetric. So if A were a Lie algebra, you would have, if you calculate this thing here, since A is skew symmetric, this would be f of A alpha beta minus rho of beta f times alpha. But then, since A might not be skew symmetric, then we want it to satisfy this condition with another tensor here. So let's just call it lambda in the differential of f times alpha times beta. So no, that's problem. So again, you call rho is a bundle map from E to T of M, called Yanko. And now lambda is a map from T star of M times E times E to E. I think this definition is due to Grabowski, if I'm not mistaken. And this is called the Coenco. I'm calling it the Coenco. I don't know how other people call it. So now it's basically the same thing as a Lie algebra. It's the non-skew symmetric version of Lie algebroid, still satisfying the Jacobi identity. But now, if it's a Lie algebroid, then lambda is identically 0. But in general, we don't ask that to be true. So, yes, sure. A lot of that. This is sure a lot of restriction. Yeah, there are a lot of restrictions. So it's not very easy to find examples, right? So let's give you some examples. So first example, of course, I already mentioned, it's Lie algebroids. So for example, T of M or any Lie algebroid. A Lie algebroid is an example where the Yanko is identically 0. I mean, but you don't want to know the examples that you already know. So the other classical example are the current algebroids. So it's basically the Tm analog of this example is you take T of M plus T star of M. This is the generalized tangent bundle. And then you put this bracket here, the current of my bracket on it. What's the current of my bracket? You just calculate. So the sections are vector fields and one forms. Sometimes you put this bracket like that. And then the definition is just for the vector bundles, you just calculate the normal Lie bracket of vectors. And then you add you calculate this one form here of x with beta, and you contract in y the differential of alpha. So this is the current of my bracket. And in this case, if you wanted to calculate lambda, so this is current of my. If you want to calculate lambda, then lambda of d of f times x plus alpha y plus beta. This is simply the natural inner product between these two here. So I write it as ix of beta plus iy of alpha times the differential of f. So this is a section. This is seen as a section of t plus t of star of m. So this is an example where lambda is not 0, and this satisfies the Jacobi identity. That means these are the basic space for Dirac structures. There is still some other examples that are some variation of these examples. I want to talk about. Oh yeah. So this is the main example. This is called a current algebroid. So what's a current algebroid? So you start with a vector bundle over M, and you assume you have in each subspace here, let's call it here, like this. You have a non-degenerate. You have a non-degenerate symmetric pairing. I don't know if anyone talked about this definition before. So you have this, and then a bracket, A is going to be a current algebroid if you satisfy these conditions. Of course, Jacobi. And the other one is certain control of the symmetrization. That is given by basically that same formula I told you. So this should be the differential of alpha, beta. But this is one form, right? So you have to calculate this anchor here. So I probably wrote this wrongly before. No, this is the anchor. Okay, sorry. I thought so. So this is right. So this is a current algebroid. So it's a Laude bracket. So satisfies Jacobi, and it satisfies the Leibniz rule in this second entries here for some anchor row. So rho is a map from E to T of M, and then its symmetrization is is controlled by this term here. You calculate this to one form here, and then you use the whole star as a map from T star through to A star. And then this has to be a section on E, so you use the pairing to identify E with E star. So this is a courant algebroid. That this example here is the first example of a courant algebroid. I'm not going to tell you more examples of courant algebroid, but there are some others. So what happens? So we also have a splitting theorem for courant algebroids. And you can also state it in terms of, it's a local splitting, and then you can also state it in terms of pullbacks, just as the case of Lie algebroids. So I'm not going to define exactly the pullback of courant algebroid, but this is a result from Lie blend and my ranking. I think it's from 2009. They basically state that there is a pullback operation on courant algebroids. So this is basically, and then, so if you have under some transversality condition, the same type of transversality condition that's anchored, the submanifolds, the maps have to be anchored transverse. So if you have a map on a courant algebroid, now we represent the algebroids as this: a pair, the vector bundle, and then the pairing here as A, and then if phi is transverse to the anchor, then we have a well-defined courant algebroid over N. How many times do I have? 18. Oh, it's true. I'm going too slow. Anyway. So this is basically the relation between splitting fields and pullbacks. Here I just told you that there are pullbacks for courant algebroids, and then our result is the analog for the same theorem holds for courant algebroids. Have a courant algebroid here over submanifold A, and then you take a submanifold that's anchored transverse. Then you can again consider here the normal bundle. You can pull back everything here to a courant algebroid of this normal bundle. And then this is a local form for this model here. So you can find a isomorphism from some neighborhood of this vector bundle to P over there. This normal bundle. And this is a tubular neighborhood embedded as before. So this is the splitting theory, and this was proven in my thesis. But it's a conjunct result with Eckert and Henrique, and it's going to be published soon. So now this brings us to the question: this is a coincidence. The pullback operation here that we define here for courant algebroids is different from the algebroids, of course. But in general, if you have any Lode algebroid. And if it has a good pullback, then we probably will have a splitting theorem. And but the other problem is that the proof that we give here is also quite different from the case of Lie algebroids. I mean, it's alike, but there are lots of there were lots of transversalities and stability theorems. But this is probably going to be. I mean, you're probably going to find another solution for this, and I think Henrique will talk about some in other opportunities. I'm not sure. But we are going to find other proofs of this splitting theorems, such that it's going to be applicable for a lot more than just Lie algebroids and current algebroids. But what's going on? Why will these Lie algebroids work? I mean, why if you have pullbacks, then you have these local forms given by these maps here. I mean, of course, if you have some pullbacks, then if you know how to define the pullback of any class of Leibniz algebra or Lode algebroid, then you can ask if it studies this thing. Right? You then have this any Lode algebroid, and then you can pull back these things here. If you know how to calculate pullbacks, and then you can ask if this theorem will hold. But I mean, you could have a lot of pullbacks, different pullbacks, and maybe this theorem wouldn't hold. So I want to talk about now which pullbacks are good. I mean, what are the pullbacks that I think that will make this work? So this is a theorem. I mean, let's see. Okay. So this is a theorem that is my thesis. It's not very exploited in there. So consider Leibniz algebroid. Yeah, Lode algebroid. Sometimes I'm calling it a Leibniz algebroid. You can just think it as the same thing I defined. Consider Lode algebroid. And n over m, and take n as submanifold anchor transverse. So transverse to its anchor. And also assume that some strange space is a vector bundle. So what's this strange space? So this, if you recall, lambda it can be calculated lambda is the co-anchor is a map from theta of m times e and going to e. So you can calculate it in the first coordinate here, if you're interested, in the annihilator space of T of n inside of Tm. So this is the annihilator. And then you restrict it just to this bundle here. It's a bundle, it's just a restriction of E to n. And then you calculating this thing here, the inverse image of T of n. Which is also a bundle because of that n is transverse to the anchor. So you take a submanifold of m such that this thing here is a bundle over n. It might sound strange now. I mean, it is strange, but this is the correct definition such that this theorem works. Then, let me see. If you take the inverse image of T of n and you divide by this bundle, it will lie inside that this thing here, this restriction, it will actually lie in the kernel of the anchor restricted to n. Then this bundle has a loaded bracket. Not just any loaded bracket, but the natural one. I mean, what's the natural? You take sections of this thing here, then you can consider that they are projection of sections from E, from where inverse of T of n, and then you take this section, you extend to E entirely here. And then you calculate the bracket in here, and then you restrict to n, and then you consider it in this space. And then this will be the natural bracket. So these are some applications, some examples. So what time you attend?
10 minutes.
Okay. Let me see. All right. So you have this theorem. So basically, what does this theorem mean? This is like this is like sometimes, I mean, under some condition, some transversality condition, if you wanna see this as a transversality condition, the image of by some bundle map of some vector subbundle is a bundle. Then under some transversality conditions, you have a well-defined pullback for any loaded algebroid. I mean, of course, you just define the pullback for sub manifolds. But then you could define me. Let me add this. No, I won't add any notation. But then this pullback here, you can just define it as this structure, this natural structure in this question. And then you can use this. I mean, it's like given. It's like if you have already one natural way to define the pullback. So the pullback cannot be just anything that you want, right? Then the question is, but then again, the pullback of Lie algebroids are very different from the pullback of current algebroids. And then what's going on? I mean, if this definition, if I had some Lie algebroid here, for example, T of M, then the pullback here is necessarily a Lie algebroid. But if I had some current algebroid here, the pullback of definition is necessarily a current algebroid, right? And the question, I mean, is there a natural pullback defined for any loaded algebroid? That's the question. I mean, this defines some under contradictorialities, of course. So this is like saying, yes, it's that kind of there is. So in general, if you have some map from N to M, and so we have this loaded algebroid here, then you can just do the same thing as when you define the pullback of Lie algebroids. So you can consider this inclusion inside this product. And then here you have to consider a product structure of this with the tangent space of N. But the thing is, you don't know what to put in here. Because if you put here the tangent space of N, then this pullback will be of Lie algebroids will be Lie algebroids. But for current algebroid, in here you have to put T plus T star of M. So it's not clear what you should put in here, and then to define the pullback operation. So to define the pullback operation, you kind of have to have before a generalized tangent space in here, some type of tangent space. And I mean, so this is a problem. I mean, in general, if you want to define the pullback, then you have to tell what to put in here, and after that, you have to tell how to make this product here. So there's two things to define. But if you know what to put in here, if you know how to make this product, then you kind of have a definition of a pullback. But then in general, I mean, for example, I could put a current algebroid here and multiply it by T of n, just as a load the algebroid. I could make sense of this. And the pullback would not be a current algebroid, of course. It would not be the pullback of current algebroid that was defined by Liebler and Marenke. So the question is, what's going on? Do we have to consider some different types of algebroids inside this thing here, inside low-day algebroids? You know, it's not very clear. So I wanted to understand this. When do we have pullbacks? So why in the current algebroid and Lie algebroid case do we have pullbacks? So at first we only have these restrictions here, but we don't know how to make pullbacks in general. So let's see what's next. Okay, just to finish now. Okay, so let me give you some examples before I finish of applications of this theorem, direct application of this theorem. So in general, we have this Leibniz algebroid here. What happens if you apply it to only one point? Then this condition is clearly satisfied because you want to see if this thing here is a bundle over a point, but to be a bundle over a point, you just have to be a vector bundle, so a vector field, a vector space. So if you take n to be a point, what this theorem is saying is that so this is inside of M, and you have a Lode algebroid here. Then it's saying that you have a Leibniz algebra structure on. So the inverse of the Runkel structure, the tangent space of any of a point is the kernel, and you divide it by some strange space here, subspace. So this thing here is always, it has always a Leibniz. It has a bracket. And a bracket that's not skew symmetric but satisfies the Jacobi identity is called a Leibniz algebra. So this thing is a Leibniz algebra. Another example that I won't talk about this other example, so I will finish it now. So there are some other examples. For example, if you have this T plus T star of M, and then you consider a submanifold of this thing, and then you can calculate the pullback here, because it's a submanifold. Then every submanifold is uncotransverse, so you can make this pullback. What happens is that this pullback is canonically isomorphic to T plus T star of N. This is an easy calculation. Or in the case of T of M, this is going to be T of N. So there is a type of naturality inside this bracket. So these are the examples I wanted to. Okay, these examples are enough. And okay. So to finish, this is like this part here. So I just wanted to define what is an exact Lode algebroid. So to do that, imagine that you have, so I'll let this appear here. Oops. Imagine that you have found some subcategory of load algebroid that you have a pullback well-defined, have this pullback structure well-defined through any map, or any good map. Then, for example, and remember this time when I wanted to define the pullback for any map, then I had to kind of multiply the tangent space, the bundle, by some other thing here that I didn't know what to put in here, right? But assume that you have a pullback structure, then it's easy to find which bundle is this one. So if you have a pullback structure, so you take any manifold. So assume that you have a pullback structure. Then you can consider the projection to a point in here. Let's call it P. And then over this point, you can consider the load algebroid, the null load algebroid. And then this thing here that I didn't know what to put is exactly this pullback. So it's like the generalized tangent space of M has to be the pullback of the null structure by the projection to a point. And then, this is like the idea of exact, what I wanted to define as exact load algebroid. These are supposed to be the load algebroids that can be pullbacks, that can be generalized tangent bundles. But if you have this as a good pullback, that if the pullback commutes, and the composition of the pullback of composition is the composition of the pullbacks. Then if you consider the projection here, and then you calculate the pullback, so this also has to be this tangent space. So it's kind of, you have to have this property to any submanifold of M. You have to have this property that its pullback has to be isomorphic to this thing here. You can imagine T tilde, the generalized tangent bundle, as something that goes from manifolds to load algebroid. So this is kind of the definition of the idea behind exact load algebroid. And then, okay. So this is the last thing. So this is the definition of exact load algebroid. So a load is exact if let me just 1 second. Sure. Okay. If you have a manifold M, submanifold, any submanifold satisfy the property tau. This means that this thing here is a subbundle. It's always a bundle. Ln is a bundle. And the second is that, every submanifold is a bundle. For example, points are the pullbacks of points. You can calculate the pullback of points. And then the second one is that the pullback of points, let's change notation, of points is going to be 0. You want that the tangent space of points are 0, have to be 0. And then to finish, it's just that this is the definition of exact load algebroid. Then proposition, a load is exact if and only if you have an exact sequence. For each point. This is the anchor. And then this recovers the definition of exact current algebroids and I don't have any more time to talk, so this is all. Thank you.